Okay, welcome to this random interaction seminar by Pankaj Bhalla. Pankaj did his PhD with Navinder Singh in PRL, and then he has been doing a postdoc at CSRC in Beijing and has been visiting at position at UNSW in Australia. And today, Pankaj will tell us about a resonant photovoltaic effect in doped magnetic semiconductors. So over to you, Pankaj.
Yeah. Thanks for this introduction. So today I will talk about the resonant photovoltaic effect in doped magnetic semiconductor, one of my recent work that we have discovered a few months back, the resonant photovoltaic effect. So let me start this talk with the brief motivation that the what is the motivation behind this effect. The number one is that the nonlinear response is becoming quite rich in these days because we are very much familiar about the linear response. However, there are recent discoveries, observations, experimental observations on the nonlinear responses, especially like a nonlinear Hall effect in a system where without breaking the time reversal symmetry, people have observed the nonlinear Hall effect. So there are other experimental groups as well which are working for the nonlinear stuff. If I talk about the science perspective, basic science perspective, or fundamentally, so the nonlinear responses characterize the topological materials, and it has a connection with the topology, and it has an interband coherence, which means that due to the transition of the carriers from the valence band to the conduction band, which takes place the play of the Berry curvature effects and disorder. From the application perspective, these studies is also important because it's a directly connection with our energy harvesting things, solar cell photodetectors and the wireless networks. Now, what is missing in these studies that in the literature you have come across the AC response, which is often people have discussed without taking the disorder into picture. But if we take the disorder into picture, how the things can be occur, what the new things can be achieved. Another point is that the AC response is generally discussed in literature when the conduction band is empty. Now, if I say that the conduction band is half empty, what should be the consequences? So these are the missing points in the literature, and these are the motivation to behind the non-linear study. So let me give the brief sketch of my talk. First, I will tell about the basic introduction about the linear and the non-linear stuff. Then I will go ahead.
Sorry,
Then
Pankaj.
yes.
Yeah, so I had a question. So the AC thing that you're talking about by Das Sharma and others, that's a linear response calculation, right? Or is that a nonlinear response calculation?
No. Those are linear response.
Those are linear response calculations.
Yeah,
Okay.
yeah.
Well,
So in this talk, I will first talk about the linear versus non-linear stuff. Then I will go ahead with the higher harmonics of photocurrents, which we call as the DC currents in the non-linear domain. Then I will tell about the theory that we have used or we have developed for this particular type of effect. Then I will tell about the resonant photovoltaic effect, where which can occur only the doped materials. Kramer degeneracy should be broken. It can only generate due to the excitation at the Fermi edge. Why these points are important that I will cover in all my later slides. Then I will tell about how this effect can be experimentally observed, and then I will conclude with the future aspects based on this problem. So let me start with the basic linear versus nonlinear response. Within the linear response theory, we use the base definition like J proportional to the first power of the field. We are giving a field to a system or to a material, and we are studying everything in the terms of the response, which we termed as a conductivity, or actually it is a second rank tensor. However, in the nonlinear response, one cannot stick up to this. One has to go ahead from this definition. And let's say that we go second order stuff like EP and EC, which is proportional to the second power of the field. Similarly, for the third rank, which is proportional to the third power of the field, and so on. And the tensors will be also like a second rank, third rank, and fourth rank, so on. So why I keep here up to only second order term. There is also story about behind this. If let us assume that we are giving some AC field, rather oscillating field, e raised to power I omega t, sine omega t, cos omega t, this type of stuff. So if we have a AC field, because of the product of these two electric field terms, one can have a square of terms like a cos square omega t. And using the trigonometric identities, one can naively separate this into the two parts, one which don't have a omega, another which has a twice of omega, or you can also term it as a frequency summation in one set and frequency difference in one set. So frequency difference, that is a DC remain, because omega and omega will cancel out each other, omega minus omega, and but in the other is also twice omega, which we call as a second harmonic generation. The DC is called as a photocurrents. So we are mainly interested in the photocurrents, like giving a AC field, studying the DC stuff from there. So these things have a topological contribution, because this play of the photocurrents totally depending upon the Berry curvature stuff, Berry connection stuff, Berry physics things. It directly connect with all those things. Now, these photocurrents can further be classified into the different categories. The number one is a rectification current, where we give a AC field, we filter the signal, and we are just filter. After filtration, we are just taking care about the DC things. This generally occur below the gap scenario, or this occurs due to the below the gap scenario EG or EG plus twice of Fermi energy. Another type
So,
of current is
sorry,
a,
so Pankaj, what is EG here? I'm not sure what system you are talking about. This is a semiconductor. This is a semiconductor band gap that you are talking about?
yes. So these are the gaps, semiconductor gaps,
Okay.
like the EG. Yeah.
So what is your scenario? The valence band is completely filled and the conduction band is completely empty.
Oh, here
Is
I
that
have
the
not.
scenario?
No. In my picture, I will take the conduction band is also half filled. But here, this is for the this classification is general. This is not based on the assumption with the whether it's completely filled or half filled.
No. But then I do not understand this because I understand the gap being the relevant quantity when you are a semiconductor. When your conduction band is half filled, you are a metal. Okay,
Yeah.
so then I would think that EF would be the reasonable quantity to look at. So why are you now talking about E and EG plus 2EF? So,
Sorry. Repeat it. En.
what is the transition that you are thinking about? That's what I'm not clear. Why these are the relevant scales? EG. I have two
Okay.
bands. Really,
Yeah.
balance band is half filled, so I'm above metal. All my low energy stuff is happening around the Fermi energy of the valence band, right?
Mhm.
So now you are talking about frequencies below the gap, EG or
Mhm.
EG plus 2EF.
Yes.
So that will not allow any transitions. Why is that the scale? I'm trying to figure out how you are classifying things.
Oh, okay. So I am classifying these things based on the energy scale. Like if we are giving a field which is less than the EG, right?
Mhm.
Like the below the gap scenario, that means we are within the you can say that within the valence band only stuff. So due to that transitions occurring into the valence band within the because of the scattering and sorry.
So for this, the transitions from valence to conduction band is not important.
Yeah, in the rectification this is not, but for the other category these are playing going to
I
play a role.
okay.
Yeah. So the second
Go ahead.
current is second current is injection current, which generally occurs due to the interference effects. How we can how we can understand this? Let us assume that we have two different uh, waves or two different beams or optical pumps. So when they interfere with the, let's assume the one is with the energy h bar omega, another is twice of h bar omega. When they interfere, because the different phase shift, different phase factor in this, so they will generate some phase due to this quantum interference effects between these two waves, their electron distribution in the momentum space will not remain symmetrical in the momentum space, due to which some current will arises, which we termed as an injection current. Now, another thing is that why this is only for circular polarized light, because circularly polarized light can give rise to can give us a phase factors in the term. So that's why the injection current can only be occur for the circularly polarized light. It cannot generate with the linearly polarized light. The third current is a shift current, which is the you are giving a light or you are giving a pump or pulse to a system, and your carriers are exciting from the valence band to the conduction band. Due to the excitation of the valence to conduction band, the center of mass shift, the displacement arises. The center of mass shift takes place on the excitations, which give rise to the current that is known as the shift current. Now, in the coming slides, whatever I'm going to explain, like a resonant photovoltaic effect, this is also come into the category of the shift current, which generally occurs above the gap scenarios. And my current is also comes into this category shift current, but it is also different, that I will explain also that how why that is different, which makes it more pronounced in the for the topological materials. So with this classification, I will go ahead. So what is the experimental motivation? So there are experimental pictures as well as experimental work, as I mentioned in the motivation slide as well. There's a nonlinear Hall effect that has been observed under the time reversal symmetrical conditions for the time reversal symmetric systems for the bilayer tungsten telluride people have studied, where they have seen that the linear Hall effect vanishes. However, the non-linear Hall effect does not vanish, and it follows, rather than the following the linear variation with the voltage and the current, it deviates from this one. Another motivation experiment by experimental group, there's a non-linear anomalous Hall effect in the, again with the tungsten telluride, where they've also studied the voltage and sorry.
Can you go back to the previous slide? So I was just trying to figure. Yeah. So what is plotted here? This is the photo current, I'm guessing, on the
Yes.
y-axis, and what is the voltage? What is on the y-axis?
Y-axis is the V of twice omega.
Oh, that's the second hammer. Okay.
Yeah.
The voltage twice omega. That's the thing that you are oscillating. I see.
Yes.
You are plotting the IV curve, but now so it's done in the reverse order. Okay, fine.
Yeah.
And you are exciting at what frequencies here? These different curves are for different frequency, or what are the different curves? Black, blue, green, and red.
Okay. So these are corresponds to different gate voltage.
Different gate voltage.
Yeah,
And this is
VG. Yeah.
okay. WTE2. Okay, fine. Okay. Okay.
So another motivation is nonlinear anomalous Hall effect, where they have also.
So you're basically saying the gate voltage is essentially just changing the Fermi energy, right?
Yeah.
Okay.
So another motivation is also the other paper why for the tungsten telluride WTE2, where they have also studied this V twice omega. That's the second harmonic voltage with the V with another V square domain. And they have also studied for the transverse and the longitudinal component here. So that is also experimental motivation to study the nonlinear stuff. So with this experimental motivation, I will go ahead. So we have considered bismuth telluride. Sorry.
But Pankaj, you are not looking at the second harmonic, right? You are going to look at the omega equal to 0 piece.
Yeah. Because I am just giving this as a motivation. These are experimental motivation for the nonlinear study. So, but
I
my
understand, but the experiments are mostly in the second harmonic, right?
these experiments are on second harmonic.
So what happens? People have not looked at the omega equal to 0 piece of the photocurrent, or or are there studies there?
No. They have studied like a shift current and the injection or the this rectification currents. People have studied, but because this is a very recent stuff, I guess 3-4 years this is going on. But in the semiconductor, typical semiconductor materials, people has done in the 2000 or 2002 somewhere. But for these topological materials, they just start with just recently 2-3 years back. So several experimental groups are working on this type of materials for the nonlinear stuff. So we have considered the bismuth telluride here. The reason to consider this is that because it has it has a strong spin orbit coupling. So that is the main reason to consider bismuth telluride. Another is that the dispersion things is available in the market or in the literature, which make us reliable to understand the physics for the second harmonic or the new type of phenomena that we have discovered. So the thing is that bismuth telluride, this is Hamiltonian. The band Hamiltonian of this material is like a Rashba, which is proportional to the first power of the wave vector. If we draw the energy contour corresponding to this band dispersion, it is a circular in shape. However, based on the RP spectroscopic measurements, the band this energy contours cannot be in circular in shape. It comes into the some distorted shape, or one can call it as a snowflake shape. Now, theoretically, how this can be explained? So, if sorry, theoretically how it can be explained? Then the Liang Fu in the 2009, he has considered that if we consider that the third order wave vector term, which he has established taking the k dot p theory, expanding the k dot p theory for the higher order terms, and using all the symmetry arguments, mirror symmetry and C3V symmetry arguments. And he has considered that if we take this k cube dependent the term in the band Hamiltonian, which we call as a hexagonal wrapping term, so then the structure is coming like a snowflake shape or the hexagonal distorted structure shape, and which is equivalent to that the what RP spectroscopy has measured in their papers. So that gives a signature that this is the main term that is giving distorting the Fermi surface of the bismuth telluride material, and is quite important term. But important point here is that if you look at the positive k-axis and the minus k-axis, this structure is quite symmetrical in each other. If the symmetry is there, now the displacement of the charge carriers will cancel out each other and we will not get any signal for the current. Now the question is, how can we break this symmetry? To break this symmetry, we have considered another term into the band Hamiltonian, which is called as in-plane magnetization term, which breaks this symmetry. Now here we can see that the dispersion, energy contour is not longer symmetrical, remains symmetrical along the positive and the negative axis, due to which the net displacement will not cancel out each other, and one can expect some type of signal from this type of material. So that is also motivation to consider this particular bismuth telluride material, because here we can break the symmetry by considering the in-plane magnetization term. One can also think that what are the other means to make this to break this symmetry. One can, for in the wire semimetals, but this is in the wire materials also, one can consider the role played by the tilt is same like in-plane magnetization here. Now this will break the Kramers degeneracy and one can get a signal for that. Now for this material to study, because we can get a signal for this particular type of material, so we have established a theory. And first I will explain about the formalism that we have developed and we use for this particular effect. We start with the quantum level equation. That's the first order differential equation in the time for the density matrix. Here we have take the band Hamiltonian, which we termed as H naught. J is a scattering term. Here we have considered the disorder potential of the delta function, like a point like impurities. This is for the sake of convenience or simplicity, we have considered the U as a delta function. Another is the He term, which is the interaction with the time dependent electric field term into this picture. Now, this is a quantum level equation in the or the density matrix. Because the density matrix, we are interested into the second order domain, second order effects. So we can write this density matrix in the part of electric field like equilibrium, so subscript 0, 1, 2. 0 means it is corresponding equilibrium part, 1 corresponds proportional to the first power of field, 2 means proportional to the second power of field, and so on. Being a density matrix, one can naively separate into the diagonal as well as the off diagonal part and write a correspondingly into the terms of the field powers. Similarly, also the scattering term J, which depends on the density matrix, one can also write this scattering term as a function of the diagonal and the off diagonal stuff here. Substituting all this category separation into the main quantum level equation, one can write the quantum level equation into the two coupled equations for the nth order itself. So here we can see that this is the first one is for the D corresponding diagonal and OD for the off diagonal term. Here in the off diagonal term, we have a capital D by capital DK, which is a covariant derivative, which has the information about the Berry connection, which is RK, which is a UK, it's a product of the eigenvector with the wave vector derivative of the eigenvector in the another index m prime. Sorry, here it is not, it should not be k prime. This is by typing mistake here. So if we take this Berry connection stuff is taken care by the f off diagonal part. So that's another reason that why off diagonal stuff is important, because it takes place, it take care about the Berry connection or Berry phase extents, the how the interband coherence playing a role here. Now,
Pankaj, just for Pankaj,
yes,
one question, just
yes,
for my orientation. The when you say off diagonal, you mean off diagonal in the band index, right?
yes, yes,
That's a part. Okay, and so the disorder per se is included in this J term. That's the way I should think of.
yes.
And do you have a particular model of disorder or scattering, or you are just going to use some overall scales like tau? I mean, some relaxation time.
Yes, tau scales that we are going to use.
Okay.
So this is a
just a related question. In the first equation, the first term on the left and the first term on the right, I should think of as streaming terms that would exist even in a collisionless setting, in a setting without any interaction. Is that right? Without any disorder.
Yes.
So the first and the third, the first term in the left and the first term on the right, presumably don't have anything to do with disorder, right?
First term in the
left and first term on the right on the top.
Yes.
You don't have it numbered it. That's what I'm trying to describe. So the df dt and the e dot del f del k, those are just streaming terms, right?
Yes.
And then conventionally one puts them all together, and on the right hand side one writes down something like a collision term.
Yes.
So I'm a bit confused about the form you've written, but maybe it's just I joined a little late, so maybe you explained this earlier.
The disorder stuff
case,
is
I'm sorry.
The disorder, everything will be take care about the J.
Everything will be
take care by the J, the capital J of D and J. The second term of the first equation.
Yes,
the left side, second term in the right side. Yeah.
No, so Pankaj, okay, that question is that normally, you have these streaming terms, and on the right hand side you just write down one collision integral and so on. So have you now just separated out the collision?
Yeah, that's my question. Yes, thank you.
That's the question. So, for example, can you show us something with what JD looks like? That would
okay. Just let me. So we have just assumed that the J diagonal of f of diagonal is like under a relaxation time, like f diagonal by tau.
Okay.
Yeah, this is considered in the left hand side here. However, for the right hand side, which is a J diagonal f of off diagonal, we have not considered this assumption over there.
So how does that JD of off diagonal, that will be modeled by something?
Yeah, why this we have not changed? Because this depends on the off diagonal, and we know that the off diagonal has a very connection things. If we ignore this part, the off diagonal part, J diagonal of F off diagonal, then the baric physics cannot play a role for the diagonal term. Here we have established that the baric physics is also contributing to the diagonal stuff.
Yes, I can see that, but I'm just asking that JD, what kind of functional form are you taking for the JD of the f of diagonal? It's the same function. It's a f of diagonal over tau. Is that
No,
what you
no,
are?
no, no. Here we have not taken that
Tell
one.
us what this JD looks like later. Then we don't need to look at it now.
In my slides, I have not put the actual form here because it's quite big. But in my paper, it is there because it has some 4 or 5 terms. It will be quite complicated term for the J diagonal F of diagonal here.
But how do you get that? I'm just saying when you write down the JD of FOD, is there some physics that goes into writing it, or is there some microscopic derivation?
Here we
Because
have a
familiar with having the JD, okay, as a relaxation time, some Boltzmann equation type stuff.
So this equation, the JD F of diagonal, in the earlier slides, I showed the expression of J within the first Born approximation, right? In the terms of the U.
Maybe you can you just go back
Yeah, sure.
to that
This
slide
this
just for a while.
expression, this expression. So this is for the row, but here we are taking that the function is f of diagonal, and we are taking the diagonal part of that thing.
Okay. Why are you? What is the justification for using the same J on the off diagonal thing? That's what I'm trying to figure out.
So this J is a function of the row here, density matrix, which has a diagonal as well as off diagonal stuff, both the things, right?
Yes.
So we have separated this into the different categories, like diagonal, off diagonal, these things.
I see. So, and then for the diagonal piece, you have not done all these complications.
Yes.
I see. Okay.
Yes.
Okay. So Kedar, does that answer your question? Or
yeah, I think I get the rough picture.
Yeah.
Yes.
Okay, go ahead. So, yeah.
Okay, fine. So with this kinetic equation, coupled kinetic equation, and using the Hamiltonian, solving this equation, we come to the final expression for the off diagonal here. So I have not shown the complete theoretical part, like that the expression mathematical part here. I just write a final expression for the off diagonal current corresponding to the second order, second power of the field, which is proportional to E square here. Here we have considered the electric field also along the x-axis. One can also consider the Ex, Ey, all those things, but we have considered only Ex here in our geometry. Here we can see that the expression here gives a lot of information to us. The first thing is that it includes the picture of R plus minus. There's a very connection stuff here. The next, another thing is that this takes care about the interband coherence things. Another is that the partial derivative of the Fermi distribution with the kx, right, del f by del kx, which takes about the Fermi surface structure here. Third thing is that the tau, which is a relaxation time. And fourth thing is that we have in the denominator twice epsilon minus h bar omega, because in the Green's function, when we solve the Green function, we have a like epsilon k plus minus of epsilon k minus h bar omega, stuff like that. Here we, in the earlier slides in the bismuth telluride, when I said that the Kramers degeneracy has been broken, so twice of epsilon k here. So how we can understand this? So at t tends to 0, when the temperature is quite small, so this distribution, the derivative of the Fermi function with the kx, can be written as a Dirac delta function with the product with the dispersion derivative with the k. Now, if we solve with the delta function, this integral, so one can see that the integrand will become at h bar omega twice of epsilon f will become proportional to the tau, which means that when the tau tends to infinity, this will approach, this will diverge. So that's the reason this is only for the doped stuff, not for the clean things. So another is that if the displacement, if the Kramers degeneracy is not broken, then the displacements will cancel out each other because we will not get the twice of epsilon k here. We will get only 1 over omega square plus 1 over tau square stuff here, like in the Dirac picture we usually get.
So how do that? Have you shown us that this is the part that's not uh, clear? So this is important for your everything, right? That
Yes.
degeneracy breaking gives you this epsilon plus of k. So
Yeah, yeah.
the way to see that the Kramers degeneracy breaking will give you that. And why are you breaking the Kramers? Because you have a magnetic field, or what? What is breaking
Yes.
your?
Yeah, in my geometry, in my material that I am using here, so in that geometry, the in-plane magnetization is breaking the Kramers degeneracy because that symmetry should be broken. If it is not broken, then we cannot get this particular effect, the resonant photovoltaic effect. So that is
Okay, but
a
is
essential
there some way
condition.
to understand? But if is there an easy way to see that Kramers degeneracy breaking will add this epsilon plus k there? I mean, I'm just trying to figure out some simple physical way of seeing that that's what will go and sit there, or is it there's nothing that is obvious about that?
This just we have just taken the band Hamiltonian. Based on the band Hamiltonian, just we do that by inserting the in-plane magnetization, or if you tilt a system from the, so then also symmetry can be broken. So if the symmetric is broken, then one can get this type of current.
And you are not getting epsilon plus of k minus epsilon plus of minus k. You are just getting epsilon plus of k.
No, we are getting because Kramers degeneracy broken, so we use that criteria. So that's why I have written here twice of epsilon k plus.
Oh, you have taken it to be. I see. I see.
Yes, yes, yes.
Okay, okay, okay.
So to make this effect finite, Kramers degeneracy should be broken. Another contribution that we have find out, like by feeding this off diagonal part into the diagonal stuff, we can also get the second order diagonal current based on the Berry physics, based on the projection part J diagonal of f of diagonal, and we have find that the magnitude for this diagonal part is same as that of the off diagonal part. So it just increase the magnitude twice for the particular material for the current. So for this type of this formalism, we have considered the band Hamiltonian for the bismuth telluride, taking all the stuff here into the based on the parameters for the bismuth telluride. We have find that the second order current corresponding to the h bar omega energy scale, we have find that it gives a peak at some particular energy scale. That's the reason we put the name resonant here. So the peak is at the particular energy scale. That energy scale is twice of Fermi energy, EF, which we have seen also in the earlier expression corresponding to the second order off diagonal current. We can see that this peak is also increasing with the changing in the lambda. The lambda is a warping coefficient. That means if we distort the Fermi contour more and more, one can get a more current. Another point is that the in-plane magnetization, which is breaking the symmetry. So if we make the asymmetry more and more, again one can enhance the peak. We have find that this current in the certain assumptions, that this plot is for without any assumption, but in certain assumptions we have seen that the current is this current is only when we have both the warping as well as the in-plane magnetization in the picture. If one of thing is absent, there will be no current at all. That means the distorted Fermi surface and the asymmetry. Both should be there into the picture. So blue curve.
Here's what I do not understand. I understood that the Kramers need to be broken to get to this. Why do you then also need the distortion? I mean, I can break the Kramers by just putting in the in-plane magnetic field, right? That you are saying will not give rise to this effect. So it's not just Kramers breaking. You need something more.
Yes, the Kramer degeneracy, without Kramer degeneracy, as I mentioned, that is a mandatory. But under certain assumptions,
So
like
what are the I'm just trying to
assumptions, I mean, say that when I said that a Dirac delta function, I take the small temperature domain t tends to 0 analytically. If we take those assumptions, we find that this is coming as a proportional to the second order of the lambda and the m, that is m lambda square. So in that way, I am just saying that because analytical calculation gives a picture that it is proportional to the first power of the in-plane magnetization and the second power of the lambda, which is a warping coefficient. Earlier, people have said that the other, not resonant, but other type of photovoltaic effect is without in-plane magnetization is proportional to only the first power of the lambda, which they termed as a shift current because of the difference into the Berry connection charge distribution between the valence and the conduction band things. So, but here we have said that if we have in-plane magnetization and warping both in the picture, only then this effect arises in our geometry that we have considered. Like geometry, I mean to say that we have considered the field is along the x-axis and the current is also measuring along the x-axis.
So I'm just trying to figure out how the distortion feeds into your equations. I hear what you are saying. I'm just trying to figure out what is physics-wise how the distortion plays a role. Is that I understand from your equations that that's what is coming up. So if I don't have the distortion, I would have just circular Fermi surfaces, right?
Yes.
And then you are saying that circular Fermi surfaces will give me 0, even if I have in-plane magnetic.
Yes, yes. Okay. So this is also based on the symmetrical arguments because in the Liang pool in the PRL 2009, they have established that if we have a warping term, it's a lambda distortion term here. So this just reduced the mirror planes, infinite mirror planes to the three mirror planes.
Okay, so you need that mirror
symmetry. Yes.
Okay.
So now this is a lambda is a theoretical parameter, but for experimentally they cannot tune the lambda. So how they can tune this current? So for them, so they can tune the Fermi energy by doping. So we have plotted this blue dot our this peak value corresponding to our results. There's a blue dot. Red is corresponding to the quadratic fitting. So we have seen that when the Fermi energy is high, so this deviates from the quadratic fit, which means that by increasing the Fermi energy, one can also enhance the second order current. Here we have considered only 10 millielectron volt in-plane magnetization after consultation with the experimental groups. That is a maximum value they told that we can consider in experiment. So we considered only 10 millielectron volt here. For other parameter values are for the corresponding to the base metal materials. Now question is, what is the origin? So what are the key ingredients we need for this type of effect? One needs a linearly polarized light. Fermi surface should be doped because we have seen that it is proportional to the tau in certain domain, in certain limit. The system should be hexagonal wrapping is there. That means some distorted Fermi surface should be there. Fourth is time reversal symmetry should be broken. And we have considered particle hole symmetry also in our picture. So this is the same stuff here. So now how it can work out? Like if the carriers are exciting from the minus Fermi energy, minus EF to the plus EF here, because we are shining a light on the Fermi surface, it excites electron carriers from the minus EF to the plus EF, from the valence band to the conduction band. With the oscillating field, the contribution from the left and the right hand side of the Fermi surface cannot cancel out each other, which I shown with the minus and plus with the arrow sign in the upper part of the diagram. So due to which the center of mass shift arises. The center of mass shift arises because the opposite sign of the group velocity, because one has epsilon partial derivative of epsilon k plus, another is a partial derivative with the epsilon k minus. When we take the difference, the shift will be arises because this will not cancel out each other. So the center of mass shift arises due to which this current is occurring here. And one particular important message here is that this effect is only at the surface, not below and above. So this is occurring only at twice of Fermi energy, because at all energy scales this is zero, only at twice of Fermi energy, and this is only a surface effect because only occurring at the surface here. Now, how this physics point of view, this effect is different from the other effects in the literature. So people have studied the shift current, which is also based on the Berry physics, but that is purely intrinsic. But the RP, the resonant photovoltaic effect, has intrinsic as well as extrinsic. Here, extrinsic means that we have considered the diagonal part of the J as well, which depends on the off diagonal part. So in that terms, we are saying that this has intrinsic as well as extrinsic picture, but shift current has only intrinsic. The second difference is that the first order warping is there. They are proportional to only the first order warping, but we have find that this is proportional to second power of the lambda warping coefficient, and we got the peak around 260 picoampere meter per watt. However, in the literature, in the shift current, it is around 120 or 110 picoampere meter per watt. So that occurs only for the time reversal symmetric. But our effect, we have to, one needs to break the reversal symmetry, this symmetry with the in that we have broken with the in-plane magnetization. So in our geometry that we have considered, but in our formalism, the shift current is there, but geometry that we have considered, the field proportional to along the x-axis, those things, there is no shift currents. So this is also proportional to tau, which could be large. So effect is finite with the disorder. So this can be sensitive to the other disorder effects, maybe such as condo. So from the practical parts, this can also work as a lie detector with as we can probe this current with the Fermi energy. Now, experimentally, picture that scheme that we have given.
Just one second. I think there's a question. Unmesh has raised his hand. Unmesh, you can go ahead and ask.
Yeah, Pankaj, so one thing I didn't understood was that you said experimentally tuning this lambda parameter is not possible. This is something theoretical. This controls the distortion, and you said that so that we are doing this doping thing. Tune this. So I don't understand how this doping actually controls this distortion. Can you elaborate this point a bit?
Because there's a lambda parameter that we have used, so that is totally based on the theoretical aspect. There is no experimental role behind the tuning the lambda, because this term is considered just to explain the RP spectra. So they have just take the cubic term into the band Hamiltonian, just say that this relate the RP's measurement, spectroscopy measurements results. So that's why they have considered for the theoretical part, but that is not experimental with the lambda.
Yeah, but that's what I'm asking, that so experimentally what is the tuning parameter? So if someone has to measure this effect, that with increasing lambda you are getting more current, what should a experimentalist have as a tuning parameter?
The experimentally that the doping, that the Fermi surface, because the thing is the current is totally proportional to the tau, which is a relaxation time scale.
Yeah.
So with the doping stuff, one can tune the Fermi energy, or one can get the more current, because for the particular material we know that this band dispersion will come for the experimentally for this particular material will be something like this thing, distorted stuff will come. But for the theoretically, we have to put some terms to explain that this is due to these terms, this is distorted. Due to this term, it's not distorted. But for experimentally, the tuning parameter is only the Fermi energy with the tau scale, I should say.
Yes, Pankaj and Unmesh, Unmesh, Pankaj is trying to say if you are doing an experiment, there is not much that you can do to see what you are asking, change with lambda, but you can still change the Fermi energy and the density at the Fermi level, and that will change the current.
Yeah.
For your thing which you are asking for, which is lambda, for a material it's fixed more or less, unless you do whatever strain or something like that. Maybe change it a little bit.
Yeah. Thanks, Pankaj. Yeah.
Okay. Yeah. So we have given some experimental idea to observe this effect. If we have a topological insulator, if we place this on the top of the ferromagnetic layer, one can get due to the proximity effect, one can generate a in-plane magnetization. And if we shine a light on the surface of topological insulator, the carriers will excite from the valence band to the conduction band. That's why I have written here twice of epsilon f, because this effect will be arises at the twice of epsilon f, as we have seen in our expression. Now the question is can be asked by experimentalists that how the thin or thick this topological insulator should be there. We have just argued that this can be observed if we make this layer as thin as possible. But based on the other results on the literature survey, we have find that this can be possible only. Our theory can be give possible or nice results only if the thickness is greater than the 3 nanometer. The reason is that if the thickness is quite small here, then the more the tunneling effects will be arises. So we have not considered any tunneling effects in our picture. So to just avoid that thing, we have just put some limit that this is based on this thickness is 3 nanometer. Then one can ask that why I put only 3 nanometer, not 5 nanometer or 10 nanometer. This is based on the papers or the articles in the literature, based on the density matrix theory. So we have put this 3 nanometer where we have done work on the screening or the Friedel oscillation stuff by our group. So another is that can we apply this theory for the materials having a thickness less than 3 nanometer, or can we generate this type of effect? Yes, we can still generate this effect. Although I am saying that this theory is valid only for greater than 3 nanometer, but this effect can be still generated because this can be achieved with the large Fermi energy, because Fermi energy scale is quite large as compared to the interlayer tunneling strength things. So this effect can still be generated. Now, why I have not used a magnetic field? Why I am using only in-plane magnetization? The reason is because if we take the magnetic field, we can get a current, but the magnitude can be small because of the Bohr magnetron in picture. So just to increase the magnitude, we have considered the in-plane magnetization. So other materials, this work can also be, this effect can also be observed. With this, so I will summarize. We have developed the general formalism which describes the second order optical response. We have measured, we have identified or we have calculated the new sizable extrinsic contribution to the current. We got a resonance in the DC current at twice of Fermi energy, whose width and scale height can be scaled with the relaxation time scale. In this direction, one can go ahead with by taking the temperature dependence, or one can include the phonons picture into the study, where the disorder, the scattering term is playing a different type of role, so which can affect this type of current. Another is circularly polarized light. If we take because of the phase factors into this, so one can also go ahead with this this particular second order current. This can be also extended for the second order Hall response. Another is what happens in the ballistic limit. This can also be worked for the third order harmonic generation by taking the DC plus AC field, all those things into the picture. So with this, thanks for your attention.
Thank you, Pankaj, for a very nice talk. And let me first ask if anybody else has questions. Vikram or Kedar or any of the students, Pradeep.
I'm good. I don't have.
Vikram has done that. Kedar?
No, I guess I'm good.
This is your
fine for me as well. I don't have any questions.
Yeah. So yeah, okay. Sudeep?
Yeah. No, it's fine for me as well. So I don't have any questions.
And anyone else has a question? Any of the students?
No, I'm fine. Thanks.
Well, I could just ask the usual, more general question. Uh, what do you sort of envisage as your main research focus in the next year or two, for example?
Sorry.
I'm just saying a more general question that's kind of usual in this context is, what do you envisage as your major research focus in the last year or two? I mean, do you have some clear ideas of what you would like to do?
Yes. Uh, I have a clear idea that what I am going to do in the coming years.
Yeah.
So the one is that in the non-linear domains only. So my focus is to consider that as I mentioned in the outlook as well. So I am working on 2, 3. That's clearly in my mind.
Okay.
So the first let me talk about the third order generation. So
Okay.
the idea in my picture is that if we take the DC plus AC field together, so we can get a signal or some type of signal with the proportional to the E omega, but EDC. So third type of picture. So I am expecting that if I take that type of scenario in picture, I can get a signal or I can get some new type of current for the third harmonic generation, and that can give a peak at all order rather than only second order. It should give a peak at all order, third order, fourth order, and so on. So that is a one picture in my mind. Another project that is in my mind to consider the phonon picture into this. If we take the phonon interactions, whether phonon or electron phonon, all those things into picture, so how the physics is going to play a role into this resonant photovoltaic effect. Because here, for a simplicity, I have considered only the point like U as a delta function. But if I take a complicated the interaction, electron phonon things, so how the temperature dependence is going to play a role in this particular type of effect. So that is also the clear idea in my mind, that 2 projects. The third project that is in my mind is the second harmonic generation. So in my scenario, I have considered focus only here is the DC current. But I know that what things is going to come for the second harmonic generation, because I have my theory has idea about the twice of omega picture as well. So if we have a second harmonic generation, how the things is going to play within the second order electric field term and the third order electric field term, because the second harmonic generation can arise in the second proportional to E square term as well, E cube term as well. So that is the 3 projects are direct in my mind. 1 or 2 maybe also another is in my mind is, but I have not looked much for that. That's a Kerr effect and a Faraday rotation effect that is also in my mind, that how these things can be taken care in this within this formalism.
Okay, very good. I guess this is a kind of an interesting area because people have also been proposing that nonlinear AC responses can be unconventional probes of strongly correlated materials as well, where you may not have the kind of description you have in terms of equations that you wrote down, but one could instead just say we don't know how to calculate it, but we can ask what property it relates to. So that's also something one can. Good.
Yeah, I was pretty much going to go there with that. So have you thought about how to include interactions in your picture? Basically, because of the reasons Kedar just kind of pointed out, this thing is in general also heating up in the, let's say, strongly correlated, maybe spin liquid type stuff and so on and so forth. So do you have any thoughts on how one can, of course you will lose analyticity, but that's okay, but is there any way of including electron interactions, let's say, within your formalism? Have you given any thought to
that? Right now I'm just taking the electron phonon, honestly saying the electron phonon into this U terms, and checking that how the contribution by the J, even in the linear response. If we forget about the nonlinear, first I should know about the linear response within my formalism. So the electron phonon picture is taking. But I have one query about this, that what should be the form of electron phonon matrix elements. That is a idea, because I can use in the literature for the different materials they have put the form of the electron phonon matrix. But what is the motivation to consider that particular type of electron phonon matrix, that I'm still reading or digging out, that why only this type of matrix element should be there to understand the electron phonon stuff into the transport.
Okay.
So this is just a thing that in my mind right now.
One more question. This is roughly the same as doing Kubo formalism, or this is more than Kubo formalism because you're keeping some coherence, stuff like that?
Yeah, this formalism is analog to the Kubo.
Analogous to the Kubo. I mean, in principle,
Yeah,
I looked at the full matrix and just worked out with that by some big magnetization, and I could work out in principle the full answer, right? Okay.
Right.
Okay, so if there are no, so again, if there are no other questions, then let us thank Pankaj once again.
Thank you.
Okay, thank you, Pankaj.